Today we're going to talk about exponential growth and decay. An exponential function has the form y equals a times b to the x, where a is not equal to 0 and the base b is a positive real number other than 1. The parent function for exponential growth is b to the x, where b is greater than 1. If a is greater than 0 and b is greater than 1, then y equals a times b to the x is an exponential growth function, and b is the growth factor, also known as the multiplier. For exponential decay, your parent function is b to the x, but b is between 0 and 1. And if a is greater than 0 and b is between 0 and 1, then y equals a times b to the x is an exponential decay function, and b is the decay factor, which would be a fractional multiplier. Exponential functions have a horizontal asymptote. Horizontal asymptotes give us end behavior, or what's happening at the end or ends of the function. For the parent function of exponential growth and decay, the x-axis is an asymptote of the graph. An asymptote is a line that a graph approaches more and more closely. The domain for exponential growth and decay is negative infinity to infinity, but the range is from 0 non-inclusive to infinity. Remember, 0 is the asymptote. Y equals 0 is what the graph is approaching but never touches. The main points of exponential growth and decay would be 0, 1, and 1b. Tell whether each function represents exponential growth or exponential decay. Then graph the function. Y equals 2 to the x. B is equal to 2, which is greater than 1. When b is greater than 1, we have exponential growth. Let's plug in the table of values. 2 to the negative 2 means 1 over 2 to the positive 2, which would be 1 over 4. 2 to the negative 1 is 1 over 2 to the positive 1, which is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, and 2 squared is 4. Graph these points. Now let's think about it. 2 to the x equals 0. Is there a solution? No, there is not a solution to this. 2 to the x will never equal 0, which is why this graph does not touch or cross 0. You will also not get a negative if your base is positive. A negative exponent only changes the side of the fraction bar. It never changes the sign of the number, which is why you have a horizontal asymptote at y equals 0. This graph uses all x's, so your domain is negative infinity to infinity, and your range is 0 not inclusive to infinity. Go ahead and graph 1/2 to the x. Is that growth or decay? That one's decay because 1/2 is between 0 and 1. 1/2 to the negative 2 is really just 2 to the positive 2. 1/2 to the negative 1 is 2 to the positive 1. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 to the 2 is 1/4. Graph these points. And again, we have an asymptote at y equals 0, with the same domain and range as y equals 2 to the x. That domain and range do not change unless you have horizontal or vertical shifts. Some real-life quantities increase or decrease by a fixed percent each year, or some other time period. The amount y of such a quantity after t years can be modeled by one of these equations. R is equal to percent expressed as a decimal. For an exponential growth model, we would take y equal to a, the initial amount, times 1 plus r to the power of t. The quantity 1 plus r is the growth factor. For exponential decay, we use 1 minus r, where 1 minus r is the decay factor. The value of a car y in thousands of dollars can be approximated by the model y equals 25 times 0.85 to the t, where t is the number of years since the car was new. Is this exponential growth or decay? The base of your exponent b is 0.85, which is between 0 and 1, which means this equation represents exponential decay. Identify the annual percent increase or decrease in the value of the car. Because this is exponential decay, our decay factor is 1 minus r. 1 minus r is equal to the base of our exponent, 0.85. Now solve for r. The rate of decay for the car is 0.15. As a percent, 15%. So the annual percent decrease of the value of the car is 15%. Estimate when the value of the car will be 8,000. We're looking for when does 25 times 0.85 to the t equal approximately 8,000. So try plugging in some values of t and see which one gives you the closest result to 8,000. When I plugged in t equals 2, I got y equals 18.0625.
Now remember, this is in thousands of dollars, so that'd be about $18,000. That is not 8,000, so I'm going to need to go further than t equals 2. Let's try maybe t equals 6. When t equals 6, y is equal to 9.4287, so that's 9,000. We're getting closer to 8,000. Let's try t equals 7. Y is approximately equal to 8,000. So after 7 years, the estimated value of the car will be $8,000. In 2000, the world population was about 6.09 billion. During the next 13 years, the percent increase each year was about 18%. Is this exponential growth or decay? Well, that special word increase helps us know that this is exponential growth. Write an exponential growth model giving the population y in billions t years after 2000. T years after 2000, so at t equals 0 is the year 2000. And at the year 2000, y, the total population in billions, was 6.09. In our exponential model, a is equal to the starting value. We have an initial population of 6.09 billion, so a is 6.09. R is the rate at which things are changing. There's an increase of 18%, so in this case, r would be 18% as a decimal, 0.18. Because this is exponential growth, our growth factor will be 1 plus r, which makes our exponential growth model equation y equals 6.09 times 1 plus 0.18 quantity to the power of t. Simplify the growth factor, and this makes sense because if we put 18% as the base of our exponent, then we would get 18% of the initial value, not 18% added onto the initial value. That 1 plus, make sure you add it on to the initial value. Estimate the world population in 2005. 2005 would be 5 years after 2000, so at t equals 5. When I plug in 5 for t, we get 13.9324 and so on, which I'll round to be 13.9 billion. Estimate the year when the world population was 7 billion. 7 billion seems closer to the year 2000, so maybe I'll plug in t equals 1 to represent 2001 or t equals 2. Y of 1 is approximately 7 billion. So in around the year 2001, the world population was approximately 7 billion. For compound interest, how can you figure out how much money will be in an account with interest compounded n times per year after t years? So if you get a certain interest rate, how many times do they apply that interest rate? Like, when do you get the interest on your account? Do you get it based on the money in your account after every year, after every 6 months? When does this compound? Our formula is A equals P times 1 plus R over N quantity to the NT. P is the initial principal or amount deposited in an account. R is the annual interest rate expressed as a decimal. N is the number of times per year it is compounded, T is the number of years, and A is the amount in the account after T years. The amount Y in grams of the radioactive isotope chromium-51 remaining after T days is Y equals A times 0.5 to the T over 28, where A is the initial amount in grams. What percent of the chromium-51 decays each day? For number 4, we're looking for the decay factor. First of all, we need to know the base of our exponent. But our exponent is t over 28, not just t. So let's rewrite this. Instead of t divided by 28, I'm going to rewrite my exponent as 1 over 28 times t. Now I'm going to use a calculator to get an estimate of 0.5 to the 1 over 28. Which is approximately 0.9755. Here is the real base of my exponent t. And since we already established that this is decay, our decay factor is 1 minus r, which is the base of our exponent, 0.9755. The rate at which the chromium-51 decays each day is 0.0245. As a percent, that would be 2.45%. You deposited $9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years when the interest is compounded quarterly. P is the principal or the initial amount in the account. You deposited $9,000, so that's P. Your annual interest rate is 1.46%. Expressed as a decimal would be 0.0146. We're finding the balance after 3 years, so T is equal to 3. And the interest is being compounded quarterly. Quarterly means 4 times a year. Plug this into your compound interest formula. And we get 9,402.2106 and so on, which is approximately 9,402.21. In fact, we don't need the approximately equals to because this is money and we don't use more decimal places for money anyways. So the amount of money in the account is $9,402.21. Exponential growth and decay are super relevant to real life. And there's our summary of exponential functions and exponential models.